Assalamualaikum. This is chemistry 11th and our today's topic is or today's lecture is about these molecular orbital diagrams of various of the molecules. Now we have discussed some examples of these some molecular orbital diagrams of certain molecules we have already discussed. Now let me give you a few more examples to so that you can understand it fully fully that how this the filling of electrons takes place in these molecular orbitals and how different molecules are formed as per this molecular orbital theory. Now today I would like to give you the example of this lithium molecule. Now as far as this lithium molecule is concerned, you know that its atomic number is 3 and its electronic configuration is 2s1 and 1s2 and 2s1. Now we have got a total of 6 electrons which are to be filled now in these molecular orbitals. Now and these as I have told you that the filling takes place in accordance with Auber's principle. It takes place in accordance with Handel's rule and Pauli's exclusion principle. Now the this molecular this orbital configuration of lithium molecule, it is a sigma 1s2 and sigma star 1s2 and then we have got a sigma then we have got this is sigma 2s2. You can see this is the these are the atomic orbitals of lithium. These are also the atomic orbitals of the lithium, and these are the resulting molecular orbitals of the lithium molecule Li2. Now you can see this is 1s you can see it is 1s. This is 1s and this 1s atomic orbital of this one lithium atom. This is 1s atomic orbital of another lithium atom, and when the two combine or they overlap, they give rise to the formation of two molecular orbitals. One is the bonding molecular orbital, that is sigma 1s, and then you got the antibonding molecular orbital, that is sigma star 1s. Now since we are the first the 1s orbitals of these both 1s atomic orbitals of both these lithium atoms, they are completely filled. So we have got 4 electrons, so 2 of which are filled in this bonding molecular orbital and 2 go to the antibonding molecular orbital, that is sigma 1s. Then we have got the second shell. In second shell we have got this 2s1, that is we have got a single we have got half filled atomic orbital. Now this half filled atomic orbital, that is 2s1 of this this helium atom and 2s one of other helium atom, they again combine or they overlap, giving rise to another two molecular these orbitals. You have got sigma 2s and sigma star 2s. Now since we have got 2 electrons, now both these electrons, they will be occupied by this they will be filled in these sigma 2s bonding molecular orbital. Since this antibonding molecular orbital sigma star 2s, it has got very high energy, so electrons will be occupied by this bonding molecular orbital. So the bond order of the molecule is, as you can see in this case, we have got 2 bonding electrons over here, 2 bonding electrons over here. So we have got total of 4, total number of bonding electrons are 4, and we have got 2 electrons and that they are in the antibonding molecular orbital. So we have got 1 by 2, 4 minus 2, that is equal to 1. So we can see here that there is a single bond that exists between 2 lithium atoms in lithium molecule. And now as far as this molecule, from this molecular orbital diagram of this lithium molecule, we can say we don't have any unpaired electrons. So this molecule, it is diamagnetic in nature. Then we have got this another example I have shown here. It is nitrogen. Now again, we electronic configuration of this nitrogen atom, it is 1s2 2s2 2px1 2py1 and 2pz1, and we have got 3 now half filled these atomic orbitals. So again here these are the atomic orbitals of one nitrogen atom. These are the atomic orbitals or the of other nitrogen atom, and these are the molecular orbitals which result from the overlap of these atomic orbitals from the two nitrogen atoms. Now you can see here, I have not shown here the first shell, that is K shell. So I have shown here, this is 2s atomic orbital of one nitrogen atom. It is completely filled. Similarly, this is 2s atomic orbital of other nitrogen atom. It is also completely filled. So we get from these two atomic orbitals, we get two molecular orbitals. This is sigma 2s bonding molecular orbital. This is sigma star 2s anti-bonding molecular orbital. So we have got four electrons, two of which go to the bonding this sigma 2s bonding molecular orbital, and two are filled in sigma star anti-bonding, that is anti-bonding molecular orbital. Then we have got this 2p subshell. So in the p subshell of the nitrogen atoms, we have got there are three half filled atomic orbitals. Similarly, in this nitrogen atom, we have also three half filled these atomic orbitals. They again overlap and they give rise to the formation of these molecular orbitals. We can see over here, and we can see here, this is pi 2p x, this is pi 2py. These are the bonding molecular orbitals. Then we have got this sigma 2pz. Since the symmetry of the symmetry, we are considering the symmetry of the molecule, that is the internuclear axis, that is the axis between the two nuclei. It is taken along this z axis. That is why this is 2pz. It gives rise to the formation of this sigma bond, whereas this px and py, they give rise to the formation of these lateral overlapping. So we get pi 2px and pi 2py, and these are formed by lateral overlapping, whereas sigma 2pz, it is formed by the direct or head-on overlap. So we get also these anti-bonding molecular orbitals, that is pi star 2px. Then you got pi star 2py. Then we have got sigma star 2pz. Now the six electrons which are coming from these atomic orbitals of the two nitrogen atom, they are filled in these bonding molecular orbitals, and that is sigma 2px and sorry, this pi 2py, pi 2px and pi 2py, and you got this sigma 2pz. Now this molecular orbital, this configuration of nitrogen molecule can be shown as you can see over here. This I have not shown. This is K shell, that is sigma 1s2, sigma star 1s2. Then you got sigma 2s2. Then you got sigma star 2s2. Then you got pi 2px2, pi 2py2, and you got sigma 2pz2. Now we don't have any unpaired electron in this nitrogen molecule. That if we look at the molecular orbital diagram of this nitrogen molecule, we don't have got any unpaired electrons. So this is again a diamagnetic molecule. Now the bond order in this case is we have got here 10 bonding electrons. That is K. I have not shown here K shell. That is the first shell, rather I have shown this L shell. So if we count the total number of bonding electrons, they come out 10 bonding electrons are there, and we have got anti-bonding electrons are they are 4. You can see two anti-bonding electrons are present in this sigma star 2s. Similarly, we have got sigma star 1s. So 2 and 2, that is 4 electrons. So bond order comes out, it is 1 by 2, 10 minus 4, that is 6. So that means in the molecule of this in nitrogen molecule, we have got a triple. There is a triple bond. That means there are two nitrogen atoms, they are linked together by means of a triple bond. This suggests a very high bond dissociation energy, because since we have got three these bonds in the molecule of nitrogen, one is sigma and two are pi bonds, so it has got a very high bond dissociation energy, and this bond length is also very small. So so experimentally determined values or bond association energy, it has been calculated for this nitrogen molecule. It is 940, it is 945 kilojoules per mole, and the bond length has been, it has been calculated, it is 110 picometers. Now, so we can see from it is bond association energy value, that is 945, and it is bond length, that is 110 picometers. This molecule is very stable, and rather it is quite unreactive. Then similarly we have got the molecular ions of this molecular ions of nitrogen molecule are formed when it loses or gains electrons. Now you can see this nitrogen molecule, when it loses an electron, it forms N2 plus, and when it gains electron, then it forms N2 minus, and when it gains 2 electron, then it forms N2 2 minus, that is divalent. This is divalent anion. Now in case of this nitrogen molecular nitrogen, this is cation. Now it has got a bond order of 2.5, and this is paramagnetic in nature. Although we see the molecule of nitrogen itself, it is diamagnetic. And now similarly we can see this nitrogen, this molecular anion, it is formed when this nitrogen molecule, it gains one electron. You can see here the bond order is here, it is 2.5 again. So we have got one extra electron in the antibonding molecular orbital. So 10 minus 5 divided by 2, or we can write this is 8 minus 3 divided by 2, that is 2.5. This is also paramagnetic. Similarly we have got N2 divalent, which is N2 molecule that has got, which is divalent negative. Now in this case we see bond order is 2.0. This is also paramagnetic in nature. Now these can be well understood if we draw these molecular orbital diagrams of these ions, that is N2 plus, N2 minus, and N2 2 minus. Now you can see the stability decreases, that is N2 molecule, it is more stable than N2 plus is equal to N2. These two are equally stable because they have got a bond of order of 2.5. This has also got a bond order of 2.5, whereas this divalent anion, that is a molecular nitrogen molecule which is divalent negative, so it has got a bond order of 2.0, so it is least stable, whereas the molecular nitrogen itself, it is more stable because it has got a bond order of 3. Then again we have got this oxygen molecule. Now in case of oxygen molecule, we see again the electronic configuration of this oxygen is it has got 8 atomic numbers. So 1s2, 2s2, 2px2, 2py1, and 2pz1. Again we have got two half filled these p orbitals, that is py and pz. Now if we draw the molecular orbital diagram of this oxygen molecule, you can see here these are the atomic orbitals of the two of the two oxygen atoms. You have got a 2s2 here, then you have got it here 2p, this is 2px2, y1, and z1. Similarly for this oxygen atom, we have got this 2s 2, this is 2s2, and this is 2px2, 2py1, and 2pz1. Again I have not shown here this the K shell, I have not shown here. So these are the resulting molecular orbitals. Again we see that these since they are two completely filled atomic orbitals, that is 2s and 2s of other nitrogen atom, they overlap and they form two types of molecular orbitals. You have got bonding and anti-bonding. Now we have got 4 electrons, for 2 of which go to the bonding sigma 2s, that is bonding molecular orbital, and 2 are filled in the anti-bonding, that is sigma 2s, and this molecular orbital. Then in case of this p subshell, we have got these since 2 are completely filled and 2 are half filled. Now these p orbitals, they overlap and they give rise to the formation of these molecular orbitals. So we see we have got a total of these 8 electrons. 2 are filled in this sigma 2pz, that is bonding. Then we have got 2 are filled in pi 2px, and 2 are filled in pi 2py. Now the remaining, no, these are the 6 electrons which are occupied these bonding molecular orbitals. Now the 2 electrons, they go to this is anti-bonding 2p pi 2px, and anti-bonding this is pi 2py. So these are they remain half filled. Now the molecular orbital configuration of oxygen molecule I have shown here. This is sigma 1s2, sigma star 1s2, then you got sigma 2s2, sigma star 2s2, then you got sigma 2p z2, you got pi 2p x2, pi 2p y2, then you got pi star 2p x1, pi star 2p y1. Now from this, if we look at this molecular orbital diagram of this oxygen molecule, we see that there are two unpaired electrons, you can see, which are present in the anti-bonding these pi molecular orbitals. You can see pi star 2px and pi star 2py. So from this, it shows that this the molecule of oxygen, it is paramagnetic in nature. And bond order, you can see here, we have got a bond order of this is you can see, I have not shown here, again K shell I have not shown here. So you can see here we have got these are 2 plus these 6, that means 8 bonding electrons are there, minus 4 anti-bonding. You can see 2 are here and 2 are here in these anti-bonding these pi orbitals. So the bond order, it comes out to be 2. This shows that the bond order of this oxygen molecule, that it has got a bond order of 2. So there exists a double bond between the two oxygen atoms, and because of the presence of these two these double bonds, the molecule is stable. Similarly, you can see the molecules of oxygen are formed by the loss of by loss or gain of electrons, molecular ions. You can go oxygen, when it loses electron, it forms oxygen, this O2 plus. When it gains electron, it forms O2 minus 1, which is a superoxide. Then when it gains 2 electrons, then it forms O2 2 minus, that is peroxide. Again, you can see in case of O2 plus, the bond order is, it is 2.5, 2.5, and it is paramagnetic in nature. In case of this superoxide, that is O2 minus, bond order is, it is 1.5. This is again paramagnetic, and you can see in O2 2 minus, the bond order is 1, so it is diamagnetic. Now the order of this stability is, this is O2 plus, it is more stable than the molecule of oxygen itself, which is more stable than this superoxide, that is O2 minus, and this is more stable than O2 2 minus, which has got a bond order of 1. So this is the molecular orbital diagram of this oxygen atom. So since time at our disposal is very short, we have got a limited time, so I can't explain it fully. So this is for today. Thank you very much, very much.